Continuing section 3.3 on rules of derivatives, we're not learning any new rules today, but we will extend the ideas. And I didn't leave near enough space to do this, so I'm going to do it in the margin up here at the top. Find the derivative of y equals x squared plus 3 over 2x at the point 1, 2, two ways. First using the quotient rule, and then by dividing first, then differentiating. So this is actually just what we were talking about. And we'll be able to kind of do them in parallel and go, okay, simplifying is a little bit easier. In this case, not a ton, but in some cases, simplifying is going to be a lot easier. All right, so first let's do it by using the quotient rule. So dy dx, oops, forgot to turn the pen on. By the quotient rule will be the denominator, 2x, times the derivative of the numerator, also 2x, minus the numerator, x squared plus 3, times the derivative of the denominator, 2, all over 2x quantity squared. So then dy dx, evaluated at x is equal to 1, is going to be equal to 2 times 2 minus 4 times 2 all over 2 squared. So it's 4 minus 8 is negative 4 over 4 is negative 1. If we divide first, x squared over 2x is 1/2 x. Plus 3 over 2x is 3/2 x to the negative 1. Now, instead of using the quotient rule, we can use the power rule, the constant multiple rule, to find our derivative. So dy dx is 1/2 minus 3/2 x to the negative 2. So dy dx evaluated at x equals 1 is going to be 1/2 minus 3/2, which is negative 1. It's about the same amount of writing. It's a little bit easier if you simplify first, I think. The derivative is easier to do. And the evaluation is a little easier because you have fewer places you're putting numbers into. So, like I told you yesterday, I'm going to say it probably a dozen times. If you can, simplify the expression before you take its derivative. And I swear it comes up, I think it's on our first test. I think it's on our next test. There's one where every year there's a group of students, well, in this class it might be just one, I don't know, where they don't simplify it, and it just is ugly because they didn't simplify it first. Okay, now, going on, we can also take second derivatives and higher order derivatives. So the derivative, y prime equals dy dx, is the first derivative of y with respect to x. Because mathematicians are lazy or efficient, to take your pick, they usually just say it's the derivative, but it's really the first derivative. The first derivative's derivative is called the second derivative of y with respect to x. The way that it's written is, the simplest way is y double prime. That's the second derivative. It is the derivative with respect to x of y prime. In Leibniz notation, it would be the derivative with respect to x of dy dx, or the way that this gets shorthanded, and again, this points out the laziness of mathematicians, the d squared y I'm okay with. In the denominator, the dx really should be in parentheses, right? Because this makes it look like it's dx squared. So it's not, it's dx squared. So this too tells you you're taking the derivative twice of y with respect to x both times. So you can continue taking derivatives. The third derivative, d cubed y dx cubed, or y triple prime. Once we get past the third derivative, doing little prime marks gets a little crazy. If it had been me, I would have said, use Roman numerals. I wasn't at the meeting, so they didn't take my suggestion. But what they do is they write y, and so that it doesn't look like raised to the fourth power, they put it in parentheses. It's read y super 4, because that's a superscript as opposed to a subscript. But that's the derivative of the third derivative, et cetera, et cetera, et cetera. So let's take a look at this. Let's find the first four derivatives of this polynomial function. So dy dx is going to be what?
6x squared minus 12x plus 8.
Exactly. And we notice that when we take the derivative of a polynomial function that has a constant term in it, the constant term gets cut off each time. Also, the power of our original, this is a cubic, now this is just a quadratic. The power continues to go down. So d squared y dx squared, the second derivative, will be 12x minus 12. D cubed y dx cubed is equal to just 12. And just so we get y super 4, or the fourth derivative of y with respect to x all four times, is 0. It turns out that any polynomial function that we take the derivative of enough times, eventually the derivatives all become 0. That's true for polynomial functions, not true for other functions. Rational functions, trig functions, many of those you could take derivatives all day and it's never going to 0. All right, page 2. So an orange farmer currently has 200 trees yielding an average of 14 bushels of oranges per tree. He is adding 15 trees per year, while improved husbandry is improving average yield by 1.2 bushels per tree. What's the current rate of increase in orange production? All right, so we need a formula for production. How do you figure how many oranges he's going to get off of his farm? Just at the very beginning, forget about all the extra stuff. How many oranges is he going to get this year? No, he's got 200 trees, each of which produce 14 bushels. 2,800
oranges.
bushels, right? Units are important. is getting 14 bushels of oranges. So you take the number of trees times how much does each tree produce, right? So I'm going to say that this is T times, we'll call it yield. So the change dp d little t, the little t is for time. I guess I should define my variables over here. P is production. Capital T is number of trees. Y is the average yield per tree in bushels. And little t will be time in years. So the rate of change in orange production, dp dt, is going to be capital T times dy dt plus capital Y times d capital T d little t. That makes sense? So for the number of trees that you have, you're getting additional yield, plus your yield is going to be multiplied by, well, how many additional trees are you going to get? So that's going to be, currently it's got 200 trees. Each one of them is going to yield 1.2 more bushels. Plus his current yield is 14, times he's adding 14 trees per year. So let's see, that's 240 plus 14 times 15 is 140 plus 70 is 210. So this is 450 bushels per year. What I've just done is something called implicit differentiation. We took the derivative with respect to a variable that wasn't even there. We took the derivative with respect to time. That happens a lot. We'll get more into that later, but this is sort of an introduction to that idea. Okay? All right. Well, that's that lesson. Let's go ahead and start the other one at least. Let me give you that. Interesting. So in general, we just talked about the rate of change in the orange production. In general, the instantaneous, and sometimes they leave off the word instantaneous, rate of change of a function f with respect to x at A is the derivative f prime of A if it exists. So let's look at one. I told you guys about this one earlier in the year. If A is the area of a circle, find the rate of change of A with respect to the radius r when r is equal to 5 centimeters. Be sure to use correct units. All right, so the area of a circle is pi times the radius squared. So the rate of change of the area with respect to the radius, dA dr, so we're taking the derivative with respect to r, is going to be 2 times pi times the radius. And this is that deal where it's like, oh yeah, the derivative of the area of a circle is the circumference of the circle. And believe it or not, this is how I remember the formulas for volume of a sphere and surface area of a sphere. Because the volume, you don't need to write this down, is 4/3 pi r cubed. So the surface area then is 4 pi r squared. Because it's just the derivative. I don't know if I had that memorized before I learned calculus, or it just struck me so hard that I've thought about it every time since then. So every year when I teach that in honors geometry, I'm thinking about the calculus part of it. All right, so back to this. Then dA dr evaluated when r is equal to 5 is going to be equal to 2 times pi times the radius, which is 5, which is 10 pi. Now, you may go, well, look, what about the units? They said be sure to use the correct units. All right, what are the units of area in this particular problem?
Centimeters squared.
So square centimeters per, what's the unit of r? Centimeter. Could you shorten that to just centimeters? Yes, but I think it talks more about what's going on by saying it's the rate of change in the number of square centimeters per centimeter of change. This is also why I know you do this in physics all the time, but you know, when you do feet per square second, I'm like, what the heck is a square second? What I prefer is feet per second. It's the change in the velocity over time. That's what acceleration is. So I think the units make more sense this way. Does it take a little bit longer to say? Yes. Are mathematicians incredibly lazy? Yes. So that's why they write it like this. But I think this actually makes a lot more sense in terms of what you're actually doing. Speaking of motion, one of the things we're going to look at now is motion along a line. So this is where you have a particle that's moving. Typically, we have it moving horizontally along the x-axis or vertically along the y-axis, and it's changing directions and changing its velocity all the time. Okay? Later on in the year, we'll look at, well, what happens if it's moving two-dimensionally? That is, not just along a line. What if it's doing all kinds of crazy stuff? Can we still find the velocity? Can we still find acceleration? The answer is yes. It just takes a little bit more work. So suppose an object is moving along a coordinate line, like the x-axis or the y-axis. So that we know its position, s, on that line as a function of time t is s is equal to f of t. So some function of time gives us its position on that line. The displacement of the object over time, the time interval from t to t equals to t plus delta t is delta s, the change in position, which will be f of t plus delta t minus f of t. Well, that means then that the average velocity of the object over that time, v average, is the change in position over the change in time. F of t plus delta t minus f of t all over delta t. That should look pretty familiar to you at this point, right? What is that? Well, that is f prime of t as delta t goes to 0. That's the worst as ever. It's also the worst delta t. So the instantaneous velocity is the derivative of the position function, s is equal to f of t with respect to time. So v of t, you could write that as ds dt, is the limit as delta t goes to 0 of f of t plus delta t minus f of t over delta t, or just f prime of t. Right, if we're letting s be equal to f of t, the position is a function of time of some kind. All right, so when an object is moving forward, when s is increasing, we say that the velocity is positive, right? When an object is moving backwards, when s is decreasing, we say the velocity is negative. Remember that if we're interested in how fast an object is moving without regard to direction, we want to know about speed. Speed is just the absolute value of the velocity. Or later on when we start talking about vectors, speed is the length of the velocity vector, which is, I don't know if you guys ever thought about that, but you know how you write it like this when you're finding the length of the vector? Like if this is a vector, you write it with those absolute values. That's why it goes right back to this. Speed is the absolute value of velocity. Therefore, it is also the length of the velocity vector. Again, we'll get to vectors much, much, much later. Like, I think it's the last thing we do or pretty close to it. All right, and then the rate at which a body's velocity changes is its acceleration. Acceleration is the derivative of velocity with respect to time. So a of t is dv dt, or d squared s dt squared. Okay, we'll pick up with this tomorrow. We'll pick up with this example.